Hey guys, tonight we're going to step outside of time and space as you know it. Forget your couch. Forget the city hum. We're traveling to the literal edge of existence. A place so remote that the light just reaching you began its journey nearly 13.8 billion years ago. You are floating, completely weightless, in the deepest black you can imagine. Below you, there's no earth, no moon, just the shimmering, impossible velvet of the void. You gaze out, and it's not the dazzling pinpricks of modern stars you see, but a much older, more fundamental glow, the cosmic microwave background, HMB. This is the baby picture of the universe, a faint, uniform wash of microwave radiation surrounding you in every direction, like a warm, diffuse fog left over from the very first moments of the cosmos. Imagine the universe was a tiny, impossibly hot and dense fireball. For the first 380,000 years, it was so hot and thick a plasma of electrons and nuclei that light couldn't travel freely. Photons were constantly bumping into electrons, trapped in a cosmic game of pinball. It was opaque. Then, as the universe expanded and cooled to about 3,000 Kelvin, which is still pretty toasty, but significantly cooler than the core of a star, the electrons finally slowed down enough to combine with the protons and form the first stable, neutral atoms, mostly hydrogen and helium. This event is called recombination, or decoupling. Suddenly, the cosmic fog lifted. The photons were free to travel across space for the very first time. Those liberated photons are what you're seeing now. They started as incredibly energetic, visible, and infrared light. But the relentless expansion of the universe over billions of years has stretched them out like pulling taffy. Their wavelengths have been elongated, or redshifted, all the way down into the microwave part of the electromagnetic spectrum. That's why we perceive it as the CMB. It's truly a universal phenomenon. If you were to point an antenna at any spot in the sky, you'd find this faint, pervasive hum. It's actually about 2.725 Kelvin today. One solid historical fact is that the CMB was accidentally discovered in 1964 by radio astronomers Arno Penzias and Robert Wilson while testing a new antenna for Bell Labs. They thought the persistent noise was bird poop, no kidding. But it turned out to be the echo of creation itself. The remarkable thing you notice about this light is its astonishing uniformity. It's almost perfectly smooth, with tiny temperature fluctuations, only about 1 part in 100,000, that appear as tiny colorful patches on the map scientists make of the CMB. These subtle variations are the curious, lesser-known detail. They represent the initial density ripples that served as the gravitational seeds for everything you see today: galaxies, clusters, and superclusters. Without these minuscule wrinkles in the early universe, there would be no structure, and thus, no you. It's a reminder that even the biggest structures we know started as the smallest imperfections. As you float here, you can't help but feel insignificant, but in the best way possible. You're touching the moment matter conquered energy. You're literally bathing in the afterglow of the Big Bang, which makes your 21st century problems seem a little less immediate, right? Though you probably wouldn't survive this era, given the high radiation levels and lack of breathable atmosphere. So maybe hold off on making it your permanent residence. Historians still debate whether the smoothness of the CMB is the strongest evidence supporting the theory of cosmic inflation, a concept we'll explore later, or if other mechanisms could have produced this uniformity. But for now, just appreciate the view. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments your location and what time it is where you are. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's drift into tonight's story together. As the CMB light washes over you, you begin to drift forward in time, ever so slightly, closer to the present era. As you continue your journey forward through time, the faint, uniform hum of the CMB begins to dissipate, replaced by the sharper, more distinct points of the first stars and galaxies. Billions of years have passed in what feels like mere moments. You are now positioned in a universe that looks much more familiar, a vast cosmic web of glowing filaments and dark voids. You feel a new motion, a subtle but pervasive outward rush. It's as if every single galaxy around you is a tiny ship, all sailing away from you at once. This isn't a random scatter. It's an organized, universal retreat. This is the central discovery of the 20th century that transformed our understanding of the cosmos, the expansion of the universe. It's not that we are at the center and everything is fleeing from us. Rather, the very fabric of space itself is stretching, carrying the galaxies along for the ride. To grasp this, remember the Doppler effect. When a siren approaches, its pitch sounds higher. The sound waves are compressed, and as it moves away, the pitch drops. The waves are stretched. The same principle applies to light. When a distant galaxy moves away from you, the light it emits gets stretched into longer, redder wavelengths, a phenomenon called cosmic redshift. The more distant the galaxy, the faster it appears to be moving away, and the greater its redshift. This fundamental relationship, connecting a galaxy's distance to its recessional velocity, is now known as Hubble's law. It was formulated by Edwin Hubble in the late 1920s, a solid historical fact. He observed that the vast majority of galaxies were redshifted and that their velocity was directly proportional to their distance. You can imagine it like dots on a balloon. As the balloon inflates, every dot sees every other dot moving away from it. The dots that are farther away from a given dot will appear to move away faster, simply because there is more stretching space between them. This linear relationship, v equals h naught times d, where v is velocity, d is distance, and h naught is the Hubble constant, is the foundation of modern cosmology. A curious, lesser-known detail is that Hubble himself was initially very cautious about interpreting his findings. He referred to the relationship as a velocity-distance relation, and did not fully accept that it proved an expanding universe until much later. He was a scientist who wanted to be certain before making such a profound claim, which is a good reminder for us all, right? Don't jump to conclusions, even if they seem obvious in hindsight. This is a good joke to tell at your next dinner party. You'll be the hit of the night, guaranteed. The value of the Hubble constant, h naught, tells us the rate at which the universe is expanding. It's the speedometer of the cosmos, measured in kilometers per second per megaparsec, divided by s, divided by mpc. A megaparsec is about 3.26 million light years, so if the Hubble constant is, say, 70 km divided by s divided by mpc, it means a galaxy 1 megaparsec away from you is receding at about 70 kilometers per second. Historians still debate whether Georges Lemaitre or Edwin Hubble deserves more credit for the discovery of the expanding universe, as Lemaitre published a similar finding 2 years earlier, though in a less-known journal. As you drift among the retreating galaxies, their light stretches and reddens before your very eyes. You feel the profound truth of Hubble's law, that we live in a universe not static and unchanging, but one that is dynamic, growing, and eternally in motion. The galaxies are still receding, a silent, cosmic armada, but a new question forms in your mind. How did Hubble and his colleagues know the distances to these incredibly remote star systems in the first place? It's one thing to measure the redshift of a galaxy's light, but to know its actual distance, that's a whole other challenge. You're about to climb the cosmic distance ladder, a metaphorical series of rungs that astronomers use to measure progressively larger cosmic distances. Each rung relies on a different technique, building upon the one below it. If you slip on one of the lower rungs, all your subsequent distance measurements are wrong. It's like a cosmic Jenga tower. Get one piece wrong and the whole thing comes crashing down. The first rung, and perhaps the most direct, is called parallax. This is a solid historical fact. We've used it since the 19th century to measure the distance to nearby stars. It's based on the same principle as holding a finger out in front of your face and watching it appear to jump side to side as you close one eye and then the other. By measuring a star's apparent shift against the background of more distant stars as the Earth orbits the Sun, astronomers can use simple trigonometry to calculate its distance. This works for stars up to a few thousand light-years away. But beyond that, the shift is too small to measure accurately. So, for the next rung, you need a different method. This is where standard candles come in. These are astronomical objects with a known, consistent intrinsic brightness. Think of them like a cosmic light bulb with a known wattage. If you know how bright the bulb should be, and you measure how bright it appears to be from your perspective, you can calculate how far away it is. The fainter it looks, the farther away it is. The most famous and reliable of these are Cepheid variable stars. A curious, lesser-known detail is that Henrietta Leavitt first discovered the relationship between a Cepheid's pulsation period and its true luminosity in the early 1900s. She found that the brighter a Cepheid, the longer it takes to pulsate. By measuring the period of a distant Cepheid, astronomers could determine its intrinsic brightness and use that to calculate its distance. A brilliant and foundational discovery. As you look at these pulsating stars, you can't help but feel a little awe. They're like cosmic metronomes, ticking away their distance for anyone who knows how to listen. The Cepheids, however, aren't bright enough to be seen in truly distant galaxies. So, you must climb another rung. For the most distant galaxies, astronomers use another kind of standard candle, type Ia supernovae. These are exploding white dwarf stars that reach a consistent, incredibly high peak brightness. They are so bright that they can be seen from billions of light-years away. It's as if a cosmic firework with a known brightness went off in a distant galaxy. By measuring how bright it appears, we can calculate the distance to that galaxy, providing us with the farthest rungs on our ladder. Historians still debate whether all type Ia supernovae are truly identical in brightness, as subtle differences could introduce systematic errors into our measurements, impacting the accuracy of the Hubble constant. The cosmic distance ladder is a testament to human ingenuity and the cumulative nature of scientific discovery. Parallax gets us to Cepheids. Cepheids get us to type Ia supernovae, and supernovae get us to the edge of the observable universe. You are now armed with the knowledge of how we measure the vastness of space, and with that, you can truly appreciate the magnitude of the next challenge we face. Now that you understand the cosmic distance ladder, you can appreciate the profound conundrum that has emerged from applying it. We have the tool to measure distance, and we have the means to measure recessional velocity through redshift, which means we should be able to precisely calculate the Hubble constant h0, the expansion rate of the universe. Yet, as you look out at the cosmos, you feel a deep, frustrating tension. The universe is giving us two different answers. This is the core of the two faces of the Hubble constant, often called the Hubble tension. On one side, you have measurements based on the late-time universe, the relatively modern cosmos. This method uses the local observations we just discussed, the standard candles like Cepheid variables and type Ia supernovae, measured from instruments like the Hubble Space Telescope. These observations are direct, relying on geometric distance measurements and the brightness-distance relationship. The value derived from this method consistently hovers around 73 kilometers per second, per megaparsec. 73 kilometer, divided by s, divided by mpc. This side of the tension is often championed by teams like SH0, ES supernova H0 for the equation of state. On the other side, You have measurements based on the early time universe, looking back to the universe's infancy. This method relies on analyzing the precise patterns in the cosmic microwave background, CMB, that you were floating in earlier, remember? By assuming the standard cosmological model, LCDM, which we'll get to later, is correct and feeding the CMB data into it, scientists can predict what the Hubble constant should be today. The Planck satellite observations of the CMB consistently yield a lower value, closer to 67, 4 km divided by S divided by MPC. This 5-6 unit discrepancy, the tension, is significant, far exceeding the margin of error for either set of measurements. One solid historical fact is that the original uncertainty in the Hubble constant, in the 1970 seconds and 1980 seconds, was notoriously large, ranging wildly from 50 to 100 kilometers, divided by S, divided by MPC, leading to huge uncertainty in the age of the universe. Compared to that historical fuzziness, the current 67 versus 73 debate is a sign of incredible precision, but also of a deep, underlying problem. It's like having two extremely accurate clocks telling you the time, but they're 6 minutes apart. You know, one of them, or perhaps the underlying theory, must be off. The implications are massive. If the CMB value is right, it means something is wrong with our local measurements, perhaps a flaw in the distance ladder, or the calibration of standard candles. If the local value is right, then historians still debate whether it implies that there is a fundamental flaw or missing physics in the standard LCDM model, the entire theoretical framework used to model the early universe and make that prediction. Perhaps a new, unknown form of energy or matter was present in the early universe, or maybe gravity itself behaved differently. This is one of the most active and exciting scholarly debates in cosmology today. A curious, lesser-known detail that attempts to bridge this gap involves using gravitational waves. The ripples in space-time, created by merging black holes and neutron stars as standard sirens. By measuring the distance to the merger, using its gravitational wave signal, and measuring its velocity using light, astronomers hope to provide an independent, third measurement of V equals h0 times d that might break the tie. You might think, well, maybe the universe is just expanding differently in our local neighborhood. A slightly humorous idea that suggests we might be living in a special, slightly faster patch of the cosmic fabric. But for now, that h0 tension remains a clear sign that our understanding of the cosmos, whether early or late, is incomplete. As the universe expands around you, propelled by the mysterious tension in the Hubble constant, you start to notice something even stranger about the galactic dance. The visible matter, the stars, gas, and dust simply doesn't account for the gravitational forces at play. You watch as a massive galaxy cluster spins, and based on the light you can see, the outer stars and galaxies should be flung out into the void, obeying the laws of Newtonian gravity. Yet, they don't. They orbit far too fast, as if an invisible hand is firmly holding the cluster together. You realize that a substantial, non-luminous mass must be dictating the gravitational structure and overall density of the cosmos. This is your introduction to dark matter. You can't see it, you can't touch it, and it doesn't interact with the electromagnetic spectrum. No light is emitted, absorbed, or reflected. It is entirely transparent to you. This is why it's called dark. Its existence is inferred purely through its gravitational effects. One solid historical fact is that the Swiss astronomer Fritz Zwicky first postulated the existence of Dunkel Materie, dark matter, in the 1930 seconds when observing the Coma galaxy cluster. He noted that you are now immersed in a universe dominated by the silent gravitational scaffolding of dark matter. Yet the expansion rate, defined by the Hubble constant tension, seems stubbornly fast. You feel the truth, that something beyond matter, both normal and dark, must be at work. If gravity is the ultimate cosmic glue, pulling everything back together, why is the universe not just expanding, but accelerating its expansion? This discovery, which earned a Nobel Prize in 2011, introduced the most profound and mysterious component of the cosmos: dark energy. Imagine you've thrown a ball straight up. Gravity ensures the ball slows down as it rises. In the universe, the gravitational pull of all the matter should act like a brake, slowing the expansion down over time. For the first few billion years after the Big Bang, this was exactly what happened. But around 5 to 7 billion years ago, the universe shifted gears. Instead of the expansion continuing to slow down, it began to speed up. It's as if that ball you threw suddenly encountered an invisible, upward-pushing force that overcame gravity, causing it to shoot away from you faster and faster. Dark energy is this repulsive, anti-gravitational force, an intrinsic property of space itself. It's not matter, and it's not localized like a star or a galaxy. It is everywhere, evenly distributed, and its effect becomes more pronounced as space expands. One solid historical fact is that Albert Einstein actually proposed a similar concept, the cosmological constant, L, in his equations of general relativity. He introduced it to counterbalance gravity and ensure a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble proved the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Ironically, modern cosmology has brought L back as the leading candidate for dark energy, but now to explain acceleration, not static stability. The mind-bending truth is that dark energy is the dominant component of the entire cosmic inventory. If you were to make a pie chart of the universe's composition, dark energy would take the biggest slice, about 68% of the total energy density. Dark matter accounts for about 27%, leaving normal, visible matter as a tiny 5% sliver. You are surrounded by 95% invisible, unknown stuff. It's a slightly humorous thought. 95% of everything you're trying to understand is completely opaque to your senses and instruments. A curious, lesser-known detail is that, unlike matter, which becomes diluted as the volume of space increases, the energy density of dark energy remains roughly constant. As the universe expands, new space is created, and with it, new dark energy appears. This constant density is why it eventually dominates. As the universe grew, the pull of matter became weaker, since the distance between matter increased, while the push of dark energy remained the same, eventually overpowering gravity and causing the expansion to accelerate. Historians still debate whether dark energy is truly Einstein's cosmological constant, a constant vacuum energy, or if it is a dynamic field that changes over time, sometimes referred to as quintessence. The current observational evidence strongly favors the simple cosmological constant, a constant vacuum energy. But until we know what dark energy is, and not just what it does, it remains the most profound unsolved mystery that drives the relentless, accelerating expansion of the cosmos. You feel that persistent, outward shove, realizing you are riding on a rapidly expanding cosmic bubble. Galaxies within the cluster were moving so quickly that the cluster should have already flown apart, unless there was far more mass present than could be accounted for by BAT. The visible galaxies. Imagine trying to weigh a room full of people, but when you step on the scale, it reads 10 times heavier than the sum of everyone's known weight. That extra, unseen mass is what we call dark matter. It's estimated to make up about 85% of the total matter in the universe, while the normal stuff you and I are made of baryonic matter accounts for only about 15%. You can literally feel the gravitational influence of these invisible halos of dark matter surrounding every galaxy and cluster. A curious, lesser-known detail about dark matter is that its distribution forms the cosmic web, acting as a gravitational scaffolding. Computer simulations show that without dark matter, the initial density fluctuations in the early universe, those tiny ripples you saw in the CMB, wouldn't have had enough gravitational oomph to collapse and form the massive structures we see today. Normal matter alone is too sparse and too subject to radiation pressure to coalesce quickly enough. Dark matter created the stable gravitational wells that allowed the first galaxies to bloom. It's the skeleton upon which the visible universe is built. The current leading candidate for what dark matter actually is belongs to a category called WIMPs, weakly interacting massive particles. Hypothetical particles that only interact via gravity and the weak nuclear force. Despite decades of searching and massive underground laboratories to shield experiments from cosmic rays, these elusive particles have yet to be directly detected. It's a cosmic game of hide and seek. And dark matter is a master. Historians still debate whether the gravitational anomalies attributed to dark matter are truly caused by a new form of mass, or if they represent a breakdown of Einstein's theory of general relativity at galactic and cluster scales, suggesting the need for a modified Newtonian dynamics, MOND. But for the vast majority of cosmologists, the simplicity and predictive power of the dark matter hypothesis make it the current favorite. As you drift, sensing this overwhelming, invisible presence, you realize the observable universe is merely the glowing froth on an immense, dark ocean. You are now immersed in a universe dominated by the silent gravitational scaffolding of dark matter. Yet the expansion rate, defined by the Hubble constant tension, seems stubbornly fast. You feel the truth that something beyond matter, both normal and dark, must be at work. If gravity is the ultimate cosmic glue, pulling everything back together, why is the universe not just expanding, but accelerating its expansion? This discovery, which earned a Nobel Prize in 2011, introduced the most profound and mysterious component of the cosmos: dark energy. Imagine you've thrown a ball straight up. Gravity ensures the ball slows down as it rises. In the universe, the gravitational pull of all the matter should act like a brake, slowing the expansion down over time. For the first few billion years after the Big Bang, this was exactly what happened. But around 5 to 7 billion years ago, the universe shifted gears. Instead of the expansion continuing to slow down, it began to speed up. It's as if that ball you threw suddenly encountered an invisible upward pushing force that overcame gravity, causing it to shoot away from you faster and faster. Dark energy is this repulsive, anti-gravitational force, an intrinsic property of space itself. It's not matter, and it's not localized like a star or a galaxy. It is everywhere, evenly distributed, and its effect becomes more pronounced as space expands. One solid historical fact is that Albert Einstein actually proposed a similar concept, the cosmological constant, EL. In his equations of general relativity, he introduced it to counterbalance gravity and ensure a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble proved the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Ironically, modern cosmology has brought Lel back as the leading candidate for dark energy, but now to explain acceleration, not static stability. The mind-bending truth is that dark energy is the dominant component of the entire cosmic inventory. If you were to make a pie chart of the universe's composition, dark energy would take the biggest slice, about 68% of the total energy density. Dark matter accounts for about 27%, leaving normal, visible matter as a tiny 5% sliver. You are surrounded by 95% invisible, unknown stuff. It's a slightly humorous thought, 95% of everything you're trying to understand is completely opaque to your senses and instruments. A curious, lesser-known detail is that, unlike matter, which becomes diluted as the volume of space increases, the energy density of dark energy remains roughly constant. As the universe expands, new space is created, and with it, new dark energy appears. This constant density is why it eventually dominates. As the universe grew, the pull of matter became weaker, since the distance between matter increased, while the push of dark energy remained the same, eventually overpowering gravity and causing the expansion to accelerate. Historians still debate whether dark energy is truly Einstein's cosmological constant, a constant vacuum energy, or if it is a dynamic field that changes over time, sometimes referred to as quintessence. The current observational evidence strongly favors the simple cosmological constant, a constant vacuum energy. But until we know what dark energy is, and not just what it does, it remains the most profound unsolved mystery that drives the relentless, accelerating expansion of the cosmos. You feel that persistent outward shove, realizing you are riding on a rapidly expanding cosmic bubble, riding the wave of dark energy's relentless push. You begin to contemplate the entire shape and destiny of this vast, expanding canvas. How do scientists model a universe that contains matter, both dark and luminous, trying to pull it back, and dark energy trying to push it apart? The answer lies in a set of elegant, powerful equations that govern the dynamics of the cosmos on the largest scales. The Friedmann equations, derived from Albert Einstein's general relativity by the Russian physicist Alexander Friedmann in the 1920 seconds. These equations describe how the universe expands or contracts based on its overall density and curvature. They are the mathematical backbone of the standard cosmological model. Imagine the universe as an enormous, dynamic fluid, and the Friedmann equations are the rules dictating how that fluid behaves over time. One solid historical fact is that Friedmann developed these solutions years before Hubble proved the universe was expanding, making his work a profound theoretical prediction of a dynamic cosmos. The critical term in these equations is the density parameter, omega, which compares the actual density of the universe, rho, to a critical density. The critical density is the precise density required for the universe to be geometrically flat, meaning parallel lines remain parallel forever. The geometry of the cosmos depends entirely on this parameter. If omega is greater than 1, the universe is closed, like the surface of a sphere, with positive curvature. There is enough matter divided by energy to eventually halt the expansion and cause a big crunch. If omega is less than 1, the universe is open, like the surface of a saddle, with negative curvature. There is not enough density to stop expansion, leading to eternal expansion. If omega equals 1, the universe is flat, with zero curvature. Expansion will slow down but never completely stop. You realize that, by measuring the curvature, we can determine the ultimate fate. How do we measure the curvature? By looking back at the CMB, the ancient light from the early universe. A curious, lesser-known detail is that the size of the acoustic peaks, the characteristic hot and cold spots you first observed in the CMB, acts as a cosmic ruler. If the universe were positively curved, closed, these spots would appear larger than expected. If negatively curved, open, they'd appear smaller. The measurements from the Planck satellite and other CMB experiments consistently show that the universe is incredibly close to flat. Omega is approximately equal to 1. This finding is powerful evidence in favor of the LCDM model, lambda cold dark matter, which combines the cosmological constant, L representing dark energy, and cold dark matter, CDM. It tells us that the total energy density of the universe is almost perfectly balanced to create a flat geometry. This flatness finding raises an interesting point. Historians still debate whether the current measurement of a flat universe is a true statement about the global geometry of the cosmos, or if it is merely a local condition we observe. The simplest model, though, suggests a universe that will expand forever. The Friedmann equations, incorporating dark energy, confirm the accelerating expansion you feel. The fate isn't a big crunch. It's an endless, chilly stretching. This mathematical framework gives you a sense of cosmic destiny, elegantly written in the language of physics. You are riding on a spatially flat, relentlessly accelerating plane of existence. Now understand the overall geometry and dynamics of the universe. But the mind-bending reality of its initial moments still feels a bit messy. Why is the universe so remarkably flat? And why, when you looked at the CMB, was it so astonishingly uniform, even across regions that should never have had time to communicate with each other? These are the problems that the Friedmann equations alone can't solve. The solution, which you are now about to witness, is a theory called cosmic inflation. Imagine, the Big Bang wasn't a single, explosive event that set off a slow expansion. Instead, imagine it as a momentary, super-rapid, exponential burst of expansion in the very first fraction of a second. We're talking about an unbelievably brief period, from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds after the Big Bang. During this period, the universe didn't just expand. It ballooned at a rate faster than the speed of light, swelling from a subatomic size to something roughly the size of a grapefruit. This isn't a violation of Einstein's rule that nothing can travel through space faster than light, because here, space itself was expanding. One solid historical fact is that the theory of cosmic inflation was first proposed in the early 1980 seconds by physicist Alan Guth to solve two major cosmological puzzles, the flatness problem and the horizon problem. Let's tackle the flatness problem first. If the universe were even slightly curved in its infancy, that curvature would have been magnified dramatically as it expanded. For the universe to be as flat as we observe it today, it would have to have been perfectly, impossibly flat at the start. Inflation provides an elegant solution. It stretched the tiny, initial universe to such a gargantuan size that any pre-existing curvature was effectively flattened out, just like how the surface of a gigantic balloon seems flat to a tiny ant walking on it. You can almost feel that immense, smoothing stretch. A curious, lesser-known detail is that inflation also explains why we don't see any magnetic monopoles. Hypothetical, isolated north or south magnetic poles. Theorists predicted that these should have been created in the early, hot universe, but we've never found a single one. Inflation solves this problem by taking all the monopoles that were created and spreading them so thinly across a vast universe that the probability of encountering one is virtually zero. It's like pouring a single drop of red dye into an ocean and then trying to find that one molecule of dye later. Cosmic inflation didn't just stretch space. It took the quantum fluctuations present in the universe at that time and stretched them out to astronomical scales. These stretched out quantum ripples became the density fluctuations that would later give rise to the seeds of the large-scale structure, the galaxies and clusters we see today. Those tiny, imperfect temperature spots in the CMB that you saw at the beginning of your journey, they are the direct, fossilized evidence of these quantum fluctuations. Historians still debate whether the specific model of inflation, how it began and ended, is correct, as there are many variations, but the core idea of a rapid, exponential expansion remains the leading explanation for the universe's large-scale properties. Without inflation, the universe would be a very different and much stranger place. You can almost feel the quantum hum of that moment. The concept of inflation, that mind-bending period of super-rapid expansion you just experienced, beautifully solved the flatness problem, but it also provides the most elegant explanation for the other great puzzle you first encountered when gazing at the uniform glow of the CMB. The horizon problem. This problem is one of cosmic scale and timing, and it highlights a fundamental limitation of the standard, non-inflationary Big Bang model. Imagine two distant points on opposite sides of the visible sky, both showing the same, almost identical temperature in the cosmic microwave background. The distance between them is so vast that light, the fastest information carrier in the universe, has not had enough time since the Big Bang to travel from one point to the other. In cosmological terms, these 2 points are causally disconnected. They are beyond each other's cosmic horizon. If they've never been able to talk to each other or exchange energy, how can they have reached the exact same temperature? It's like finding two completely separate cups of coffee, brewed on opposite sides of the planet without any contact, that are nonetheless exactly 150 degrees Fahrenheit. They must have shared a common, uniform starting condition. But how? This is the horizon problem. It challenges the assumption of homogeneity, that the universe is roughly the same everywhere, by pointing out that in the non-inflationary model, the observed uniformity is physically impossible. You sense this disconnect, this profound lack of time, as you look across the vastness. Inflation resolves this with a simple yet revolutionary premise. Before the inflationary period, the entire observable universe, and much more beyond, was contained within a tiny, incredibly small region. A solid historical fact is that this region was so small that all its parts were indeed within causal contact. They had plenty of time to interact, mix, and reach thermal equilibrium, essentially attaining the same uniform temperature. Think of it like a pot of soup. If the pot is small, you can stir it easily, and the temperature becomes uniform. Then, inflation took hold. In that brief 10 to the power of -32 second burst, this tiny, uniform region was stretched by a factor of 10 to the power of 26 or more. The formerly connected regions were hurled apart at speeds that effectively made them appear causally disconnected today, far exceeding the current size of the cosmic horizon. The uniformity they achieved in that pre-inflationary moment was preserved and stretched across the entire observable cosmos. The soup was perfectly stirred before the pot exploded in size. A curious, lesser-known detail is that the regions of the CMB that appear slightly hotter or colder, those tiny, essential ripples you saw, are actually the quantum-level imperfections that were present in that tiny initial region, magnified by inflation. Without inflation, those quantum fluctuations would have stayed quantum fluctuations. They wouldn't have become the macroscopic seeds for galaxy formation. Historians still debate whether the specific energy field, called the inflaton field, that drove this explosive expansion is detectable or testable with current technology, but its existence is a necessary corollary to the observed uniformity of the CMB. The elegance of inflation is that it takes two seemingly insurmountable puzzles, the extreme flatness and the extreme smoothness of the universe, and solves them simultaneously by invoking a brief, early hyper-expansion. It provides the initial conditions necessary for the universe you are observing today. A vast, flat, and remarkably uniform place, even as it expands relentlessly due to dark energy. You are now in the modern universe, a place of accelerating expansion driven by dark energy, with its grand architecture sculpted by the ghost-like presence of dark matter. You've witnessed the universe's beginning in the CMB, its expansion through Hubble's law, the tools used to measure it, and the mysteries of dark components and inflation. All of this brings you to the final contemplation, the universe's ultimate fate. Our cosmic story, like all stories, has an ending, and it's written in the competition between dark energy and gravity. There are three main scenarios for how the universe will end, each linked to the density and curvature we discussed with the Friedmann equations. You can almost feel the cosmic scales tipping. The first scenario, The big crunch would happen if the universe were a closed system with a density greater than the critical density. Omega is greater than 1. In this case, gravity would eventually overpower the expansion, causing the universe to stop expanding and begin to collapse back in on itself, becoming hotter and denser until all matter and energy are recompressed into a state similar to the Big Bang. It would be a fiery, dramatic end, the cosmic scales tipping overwhelmingly in favor of gravity. The second scenario is the Big Freeze, or heat death. This is the most likely scenario given our current understanding of a flat, accelerating universe dominated by dark energy. Omega equals 1. You are experiencing this future already. As the universe continues to expand, galaxies will move farther and farther apart, eventually becoming so distant that their light is stretched into such long, faint wavelengths that they will be invisible. Stars will exhaust their fuel. Black holes will consume everything and eventually evaporate through Hawking radiation, and the last photons will have been emitted. The universe will become a cold, dark, empty void, stretching eternally, approaching a state of maximum entropy. This is a quiet, melancholic end, where the final gasp is not a fiery one, but a whisper of ultimate dispersal. A solid historical fact is that the concept of heat death was first described in the 19th century as a consequence of the second law of thermodynamics, long before we knew about dark energy. A curious, lesser-known detail is a third, more violent possibility called the Big Rip. If dark energy is not a constant, but instead a phantom energy with a density that increases over time, its repulsive force could become so powerful that it overwhelms not just gravity on a cosmic scale, but also the forces holding together galaxies, solar systems, planets, and finally, even atoms themselves. This is a dramatic, tearing end, where the fabric of space-time rips apart, leaving no structure intact. Historians still debate whether the equation of state for dark energy is exactly 1, which would favor the Big Freeze, or if it is slightly less than 1, which would cause the Big Rip. Our current measurements favor a value of 1. As you feel the relentless, chilling expansion, you realize that the most likely fate is a gradual fade into nothingness. The cosmic calendar is long, and the future is cold and dark. But perhaps there is a strange comfort in that. The observable universe, filled with its billions of galaxies and trillions of stars, is here now, a brief and glorious moment in a vast cosmic history. You are privileged to be a part of it.